to see the interdisciplinary and cumulative nature to some of these topics, okay? So can you guys see? Okay. So number 10, how do you think about conditions of student A? Okay, so student A, student B. Student A performed the same experiment as B. Student A collects 5 liters. What variable is that? B, okay? Student B at 25 degrees Celsius. So their temperature of collection was 25 degrees Celsius, and you're like, nope, can't use Celsius, must convert to Kelvin. So add 273. That's supposed to be 25 degrees Celsius. Whew. Okay, what is that in Kelvin? 298 Kelvin. Okay, so immediately when you write Celsius out, immediately you can just convert it to Kelvin so you don't mistakenly forget it later. Student B collects a volume of 4.85 liters at a temperature of 22 degrees Celsius. Well, here's the issue. We know we can compare volumes of gases. I can say this volume is bigger than this volume, but can I do it at different temperatures? I shouldn't, because that's not a true comparison, because at different temperatures, a gas will change size, right? It'll expand or compress. So what I must think about is how can I get these volumes to a comparable, to a place where I can compare them. So the only way I can compare them is if they're at the same pressure and same temperature. It doesn't really give me a whole lot of information about pressure until I see what. Yeah. Thank you. Sorry. What is that in Kelvin? 295 Kelvin. Thank you. So what am I going to have to look at?
It tells you STP, and since pressure has to remain constant, you can just see
right. Okay. So later on it says this person, or the theoretical yield of the experiment had a volume of 4.97 liters at STP. So if we're going to compare student A's volume to the theoretical yield, and then separately student B's volume to the theoretical yield, what am I going to have to think about that needs to be a constant across the board?
volume.
Well, volume is going to be compared, right? Because the theoretical yield of volume is this. The pressure we're assuming is a constant because it just says at standard pressure at one temperature at 1 atmosphere. I'm going to have to take these temperatures, compare it to the temperature here. Well, what's ST, standard temperature? 0 degrees Celsius, which is 273 Kelvin. Okay, so basically, I'm going to compare these volumes eventually, but I have to get the volume of student A appropriated to this temperature. So you should be able to tell me what's going to happen. At 298 Kelvin, I have a 5-liter balloon, 5-liter container of gas. So what's going to happen to this volume of student A when I drop the temperature to 273? It's going to decrease. So we already know the volume is going to be lower. So I need to now find that. So this is V1, T1, this is T2. What's the actual volume of this student A's work at this new temperature? Let's figure that out. Don't tell me the answer yet. So how do I take V1, T1, V2, and T2 and consider those as a comparison? What law smacks you in the face? Charles's law, V1, T1, and V2. So V1 over T1 equals V2 over T2. How do I solve for V2? Okay, so multiply both sides by T2. So either, now, did I show you guys cross multiply and divide yesterday? Maybe? Okay, well I'm going to show you both ways. Okay, so either you take just, T2 needs to get out of the way so V2 can be by itself. So if you multiply this by T2, why am I multiplying by T2 on this side? Okay, to isolate V2, but why can't I divide by V2 on this side? Well, because it's being divided by already, right? So you have to get rid of something, you have to do the opposite mathematical function, true? Okay, so the opposite of division is multiplication. So what you do to one side, you do to the other. So T2 cancels on this side. So V2 is equal to what variables?
V1 over T1 times V2.
So can I just put V1 times T2 on top over T1? Wonderful. Okay, so we can really easily mix those up, right? So just make sure you're staying with the variables and before you start plugging in, because if not, you'll be working too hard. So what's my V1? 5.0. Liters, look at those units. And what's T2? 273 Kelvin. And what's T1? 298 Kelvin. Can you tell this is already going to be less than 5?
Yeah.
What's this? What's 273 over 298? Greater than 1 or less than 1? Less than 1. So you take 5 and multiply by a fraction, it will be lower than that, lower than what it was. So what's that final answer? 4.97 liters. So what we just found was the actual yield of student A. AY, actual yield. Because the theoretical yield was 4, no, is that right?
No,
That's not right.
4.58.
4.58. Who my calculator was. 5.8. That's why I like to have multiple calculadoras going on.
You got the actual.
Oh, okay, yeah. So this is our theoretical yield, 4.97, that this problem gave us. What we did was we took student A's collected gas in the lab, and we were like, oh, it was at 298 here. Let's just adjust that volume to STP conditions, which was 273, and that's what they actually made at this condition. So how do I get percent yield?
You need to do your actual
And times 100,
58.
so 4.58 liters over 4.97 liters times 100, and what percent is that? 92 point what? 1%?
But then.
No, that's right. That's good. We're done. That's student A's percent yield. Yeah, that's pretty good, right? And we would do the same thing for student B. I'm not replicating my work right now. But you would do the same process, all this red, for student B. What's really the only number that's different, though?
V1 or no,
Yeah, B1. So their B1 is here. And their T1 is here. So really that number and that number, right? Yeah, those will change to be these numbers, recalculate, get your percent yield. Now, the very last part of this was like, hey, this is just a reaction in the lab. What kind of reactions? What possible reaction could this have been? So it says possible decomposition. Do you remember your decompositions? Most decompositions make a gas. Give me an example of one, Megan. So give me one of your chlorides. Like what metal chloride?
Sodium chloride.
Sodium chlorate decomposes into
Probably table salt and
sodium chloride and O2 gas. Nick, give me something else that could decompose into a gas. So we did the metal.
Chloride, right?
We said the metal chlorate. Yep.
Is there a metal oxide?
A metal oxide? Yeah, it can decompose into. Let's do sodium oxide. It can decompose into. Don't you look at that blue sheet?
Oh, I was getting it for Brandon Hanson.
Okay.
Like, in all seriousness.
Oh,
Alright,
no,
it would
I saw.
compose into. Wouldn't it just be sodium and oxygen? Without jumping?
Yeah. So binary. So sodium and
Oxygen.
O like that, like O2. Okay. Carrie, give me another.
another example would be carbonate.
Carbonate. Let's do what metal?
So that would be calcium.
Calcium carbonate decomposes into.
It would be calcium and oxygen.
Well, hold on. Let carbon go.
I was going to say calcium and oxygen, like one more.
Oh.
And CO2.
So calcium oxide. Got you. All right. And CO2. Beautiful. And that's calcium oxide. Where are my subscripts?
They're reduced.
They're reduced. They're both 2's reduced to 1. Okay. And because I can't leave this like this because it's not balanced. No, it is balanced. Never mind. I'm leaving it. Yeah. Okay. Cool. So now number 12. Okie dokie. Huh? It is balanced, right? Huh?
Oh yeah.
That's turning into.
It is balanced, right?
Yeah, it's balanced, 'cause I can see.
Oh, the first one's not balanced. Gosh, let me fix that. Hold on. All right, you guys tell me your givens for 12. Need that one? Okay, I feel better now. Thank you for that. Can't be leaving those unbalanced equations up there breaking the law. Somebody's gonna report me. The local chemist. You guys are not fun. Okay, so thanks. So, what are my givens here?
Temperature, volume, gas,
Okay. Okay, so it says, first off, hold on. I see a question actually posed first. What's the question? Calculate the temperature. So I'm like, is that T1 or T2? I'll figure it out later. And it says this nitrogen gas has a volume of 2 liters. Okay. And then it says, calculate the temperature of this gas, which is at STP. So I hear temperature of 273 Kelvin and pressure of 1 atmosphere, or 101.3 kilopascals, or 760 millimeters mercury, or 760 torr. I mean, there's all these pressure units that mean 1 atmosphere. Okay, so I'm sticking with this one. Kilopascals?
Well, you're gonna have to convert it anyway.
So just hold up, man. Hold up. Okay, so I'm normally I just go 1 atmosphere, 273 Kelvin, because it's the easiest thing to write. All right, so if this, what's the temperature if that gas at STP, which those were given collectively together, right? Yes, is subjected to a pressure of this. So now I'm writing a secondary pressure of 920 millimeters of mercury. Okay, do you see a second volume given?
No.
So are you assuming volume is changing? No, you're assuming it's constant because it doesn't say it changed. So do you need this volume here?
No.
No, it's just a distraction. Get rid of it. Okay. Now I see the equation. What equation? Gay-Lussac. So P1 over T1 equals P2 over T2. And then you're like, but where's my P1s and where's my P2s?
P1 would probably be at 1 atmosphere.
And since those went together, I have to label those conditions the same, right? So I'm calling that P1 and T1. So this must be T2 and P2. That helps you as you write it out. It's not as clear in this one who are the ones and who are the twos, but since those were given collectively together, that made it easy, and then we could proceed together. Okay. So this is where I'm going to do a cross multiply and divide. So I'm looking for T2, right? Well, dang it, that's in the denominator. That's always the hard one to get isolated by itself because you don't really know how to mathematically get that by itself. So if you cross multiply P1 times T2, you cross multiply, so that's P1 times T2, and you set that equal to the other cross multiplied, which is P2 times T1. P2 times T1. Now you're like, I got this. How do I isolate T2? Right, so that's why it's called cross multiply and divide. So divide by P1. P1 cancels. Now we can say T2 is equal to what?
P2 times T1 over P1.
Right, and now we can plug our variables in. T2 is equal to, what's P2? 920 millimeters of mercury. What's T1?
270 Kelvin.
And then what's P1?
Like 7.
Okay, so this is where we're like, oh no, 1 atmosphere, millimeter, that one of mercury. You can't use those both because they're not the same pressure units. They won't cancel. So if you're not writing your units, you may not notice that. So right. So now you're like, I know what that 1 atmosphere is. It's 760 millimeters of mercury. Easy money. Right, Kendall? Where were you at during intervention? Oh, I didn't see you during intervention. Now that made me think of that. Okay. So millimeters of mercury cancel, done. Kelvin is achieved. Tell me the calculation. Calculate. Elijah, if you've got all the baskets with PR tables and the calculators if you want one.
330
Say again.
330 Kelvin.
330 Kelvin is what I'm hearing.
And you have to put a period.
Okay, so And since I'm such a nice person, I like to give you as many opportunities as I can to practice going from Kelvin to Celsius. And the answer key, I may have established it as Celsius, right? And you were like, sneaky lady. So what do I do to get from Kelvin to Celsius? Subtract 273, and you get
57.5.
57.
For point.
Where are the 0.5?
Because they didn't do the intermediate route.
Oh, so what did you guys say this was?
330.5.
0.5. I got you. Okay, so now it makes more sense. No, yeah, Celsius. Okay.
Are you gonna do that?
I will. That would be on like multiple choice. But if it was like for your response, I probably would specify what to give me the unit in.
Oh, so you mean like if the answer was like 57.5, you put 57.5 Celsius in Kelvin?
Yep. It's an opportunity for learning. You're welcome. Okay. So, last one. This was one that was requested by my resident celebrities. I'm not sure you asking for 16, but I got you. What would be the temperature? Okay, so question. What would be the temperature? Got myself so far. That's my question. If 50 milliliters, what is that? Volume of a gas at STP. Okay, so is all this given together? Yeah, so that's all considered one scenario? Okay. Austin, will you shut my back door? So temperature and pressure are what? 273 Kelvin and 1 atmosphere. Okay. All right, so we're compressed under this pressure, 199.9 kilopascals, to this volume, 30 milliliters. All right, so what all went together?
So 273 in 1 atmosphere.
And
the 99.9, or the 199.9 and 30.
But I can't have all those in one scenario because those are two pressures.
Yeah, but you can have,
Well, I want to know who my ones are.
oh, your 1, 2,
50, 273 Kelvin, and 1 atmosphere. Because those three conditions were given together as like one scenario. So then the twos must be
199.9.
30 milliliters and the question. Okay, so if that's the hardest part, writing your units out like this as givens, which some of you did and some of you didn't, that's going to be your most helpful piece, because then it's easy peasy from here. What law is this? Combined gas law. So P1V1 over T1 equals P2V2 over T2. What are we solving for? T2. So how would I get isolated T2? What are you going to say? Cross multiply and divide,
You could
or
always flip the places between P1, V1, and T2. And if you alternate the numerator and the denominator of the second fraction. Copy that.
I don't really know how to copy that.
Well, no, but like you can always swap the second.
That's what I would call it, multiply by reciprocal.
But
It's
you can always swap the second.
but which reciprocal?
The second one, the second term.
So just multiply by T2 over
P2.
P2, but won't everything cancel?
You would just.
Not necessarily.
Doesn't
What you
make
do
any
is
sense.
you take the one on the left side and you flip that so T1 is on top and P1 D1 on the bottom.
Uh-huh.
Well, it's easier this way, and then you take T2 out and put it right there. And
It'll work.
I got you. I'm gonna cross multiply and divide because I don't want to say a mathematical new thing incorrectly. So cross multiply, and this is old school and it always works. It's worked for entities. So P1 V1 times T2 equals other cross multiplied, this one, P2 V2 times T1, and then cross multiply and then divide. Where are we dividing?
P1.
Thank you. P1, V1, P1, and V1. I mean, yeah, it's a lot of work, but it's right. T2 is isolated. Boom, boom, boom. Plug, plug, plug. Cancel, cancel, cancel. Done. T2 is equal to 199.9 kilopascals times
30 milliliters.
times.
No, sorry.
That's right. What's my temperature?
270.
273 Kelvin divided by
1.
What is that
No,
now?
101.32.
Yeah, so we have kilopascals here. I'm just going to go and take this to 101.3. All right. And 50 milliliters. All right. What units cancel? Kilopascals and milliliters, leaving us in Kelvin. Ta-da! That's what temperature should be recorded in. You guys can calculate that. Okay. Usually if I get you set up, you guys can finish calculating. All right. So let me take a break from talking to you. We'll now go to a couple of exercises between finishing up the simulation. Who's done with that already? Yeah, some of you guys are really close. Yeah. So I'm probably going to give you maybe 15 minutes right now to either finish your simulation or finish your foldable as much as you can. Does anybody need help other than Chris? Okay, I'm going to put the foldable instructions back up, okay? If you have other questions for me, I'm coming around. If Cameron, you need to go, I understand. If I leave this right here, is this, hold on. Right here?
Can you scroll down?
Austin? Boy, if you keep calling my name. Give me a second.
We just scroll down the files.
Hold on. There we go.
When you go to those like classes,
Yeah, it's TV.
Yeah, Lincoln Fire, gas, something.
I do that.
No, it's not like when, it's just the same with the pressure increase.
Yeah. So pressure increases volume. Get everything.
Okay, but mine was coming today. It should be there when I get home. Yeah, I got a black one. It's like
So it's closely related.
when we're on the balcony, we have 1 minute.
How did I miss that twice?
Like I can see the whole
Excuse me, help on anything? Is it back on? Oh, very good, very good.
Yeah.
We have a work together on this.
What is an example?
I was thinking of something with the balloon, but I couldn't
So it always.
I know.
So it was something.
If you look at my handwriting, it was like. My handwriting got progressively worse. No, yeah, mine was progressively worse as I'm writing.
But like I just know because it's on the wrong.
I know, but I don't have to draw the lines, but when I go through the mathematics of it, I'm teaching math, and so I don't want to skip a step in my head because you guys can't see the stuff in my head. So that's why I go through the elaborate division, but that is probably. Yes, we are gonna do notes on the ideal gas law in about 15 minutes, and it's gonna be these 1 through, it'll be 1 through 17. And check our website.
Do you have a
Kendall, you okay with that distraction? You good?
Lots of people in a lot of things. What about when you put them in smaller and there's less space? Pressure on the wall. Yes, and then one out of grade. Yes, one. Yeah, I guess we're gonna
I mean, you can use the same one for
Hey, how do you say Roman?
you know, what?
How do you say Roman? Oh my gosh, this is gonna bother me.
Your 15 minutes is dwindling. Who's done with their simulation? The simulation is due today. Let's get rolling, folks. Yes. Simulation is done. It goes in the box. If it's not, hold it until we get done. I have like 15 minutes of material for you. That means I have to give you 15 minutes at the end of class.
That's a fact.
Alright guys, so halfway close your computers if it is still there, and let's chat. Ready? Have your notes out because you'll be writing down some additional information about a theory, and then we'll actually do the ideal gas law together. Alright, so who can tell me what a theory is?
Something you think.
Something you can think by experiment.
Something that's been proved numerous times through experimentation and, you know, okay?
That's not to explain.
It is meant to be a very elaborate explanation of those observations that were made, right? So, like, for example, if I say, okay, guys, this right here, this is going to fall. Watch it. And, oh, darn, it fell. Natural law, stuff falls. What law is that?
Gravity.
Law of gravity, right? But then we go, well, let me tell you about the theory of natural selection. You've got this animal that has a desirable trait, and in this environment it survives, but in this environment it dies. And so all the environment, or all the animals or species that have this desirable adaptation, they survive. Survival of the fittest. These other ones, they die. Well, then they reproduce and they pass on their genes, and then the population changes its genetics over the course of thousands of years. Do you see how long-winded that is? Right? Where it's like, okay, law, right? So laws are very short, concise statements of a fact. Theories are very long-winded explanations of multiple observations seen over very, very numerous experiments where there are many people supporting that thought. So we're going to talk about this kind of long-winded theory called, come on, man, kinetic molecular theory. What do you think kinetic stands for? We're talking what you show me. What do you think kinetic stands for?
Energy.
Kinetic stands for what? Energy of motion. What does molecular stand for? So while you're I need that in the box. It needs to be labeled because I'm not going to know what that means. All right, so we're supposed to be talking about ideal gases, right? So ideal things, like raise your hand if you think you're my ideal student.
No.
Okay, so you all might think you are. You might think you're my ideal student, but my ideal student comes to me and asks questions, brings me coffee, and comes and makes sure that, you know, they got all their questions clarified. They got their homework done on time. They maybe even watched some additional videos. I mean, so here we go. Like, there's a lot of things that can make somebody ideal, right? So close your eyes and think about your ideal man or woman. Yeah, think about it. Think about all those characteristics you want. I'm not sure what you said, but I don't want to know. So you're thinking about all the ideal characteristics. Okay? Do you think they say you have 20 or 30 different characteristics that this person would have, right? Do you think you're going to be able to find that person?
Absolutely. I mean, the way technology is going, the way technology is going.
So you are optimist, okay? Now, sometimes, you know, maybe we say this ideal thing exists just because we know that we think it makes our life a little easier, right? Because you know you're going to find that thing you want. Well, in chemistry, we call things ideal gases because it makes our math easier. Yeah, you're welcome, okay? So, if we have to assume they're real gases, the math gets very, very complicated. So, we get to say, okay, if these gases, if we assume they have these characteristics, we're going to call them ideal gases because they act ideally. They behave like a gas should. So, we say gases have individually no volume. Because in a little container, let's say I have a 1 liter container, if I know it's 1 liter, I call that the volume, right? It's a 1 liter container. But if I start to have to account for every particle inside that's taking up the space, is it really now 1 liter of space to move around in? No, because the things are taking up volume. And then I get that messy math, right? So we assume they have no volume. We assume that the space they occupy is insignificant. We call their volume negligible. But for real, come on. Gases, they matter, right? They matter. So if they matter, don't they have volume? Yeah. Yeah? What? Oh, I'm boiling something. No worries. Leave it there. God, you scared the crap out of me. Nope, it's good. I am boiling. Back to me. I'm up here. I'm up here. Okay. So, we have another assumption you're writing down on the board right now. I just on the board. Did you put comments in the box? Thanks. Tell my AP students that I said hello. Did you see them?
Oh, he's gone.
Yeah,
Okay.
Have to go when he's answering us.
All right. So,
Or we change.
ready? I know. All right. So, stay with me here. Yeah. So, you saw in your particles, they were bouncing randomly on the container walls. That's the simulation you did. Now, that constant random motion, which causes collisions, what variable does that collision impact? Pressure. Pressure's definition is collisions with a container wall, right? Now, what if they weren't random? What if they, all of them collided on the right wall all at the same time? What would happen? Pressure would be huge, maybe explode outside the wall. What if they all just collided in the middle together and they never touched the wall? Pressure would be crazy different, right? So we assume that they're random so that we don't have to make those weird assumptions about where they're colliding, how to adjust the pressure. But really, real gases can be more non-random? Yeah, that's a good word for that. because of the fact that they can interact with each other through IMFs. Because let's say a gas particle attracts to another gas particle. Well, they kind of move together, right? Individually, they're hitting the side of the container. That's double the pressure. But what they attract to each other, that's half the pressure because they're not colliding with the container. So it makes our math just more difficult. It's called the real gas law. We're not going to deal with real gases, but we are contrasting them. Another assumption we make is that they have elastic collisions. What does elastic mean?
No energy is lost.
No energy is lost. So have you guys seen the little Newton's cradle thing that goes like this?
Oh, yeah.
Okay, so it's supposed to go forever, right? Well, what slows it down?
Gravity.
No friction.
Friction and what's around it? What's around it? Air resistance. Okay, that's kind of like air friction though. So we think that elastic collisions occur so we don't have to deal with speed differences and pressure differences and temperature differences. We make that assumption to keep our math easy. But for real, what happens?
There's resistance with friction and air resistance.
So I'm going to say can change with friction. Okay, I'm just trying to minimize my sentences here. So the kinetic energy can change with friction being a variable of interest. Then I've got two more for you. Ideal gases, and this is actually true for all, ideal and real. Kinetic energy is proportional to Kelvin temperature. So what we usually decide is we explain temperature as a way of portraying energy of motion. The definition of temperature is actually average kinetic energy, yes. So if the definition of temperature is average kinetic energy, it has to be established in Kelvin. The reason we can't use Celsius is because it's not our SI unit, and that many other things are proportional to Kelvin, but not proportional to Celsius, because Celsius and Kelvin are not a proportion. They're not a proportion. They're an addition. They're not a multiplication. They're not a division. Proportions are more mainly multiples of each other. All right, one more for you.
Bless you, Nick.
Okay, so yeah, and real gases. Real gas. That's a true statement for both states, actually. Real gases and otherwise. Are you on that last one for a second? No, it's not.
Bless you.
Is this good?
Bless you.
You think? Actually, that's not true. Every time I say a second term, everyone laughs. I don't know. I'm sorry. I have no volume. That was funny.
I want to see everybody.
I'm not scared.
Science.
I look more like a Martin than a
Okay, Andrew, here.
Yeah.
Okay, so look back here for just a hot second. This is going to be a hot second here. So my handy dandy assistant, Andrew, is going to stand here, and he's going to take this can, right over the beaker, beaker tongs, and he's going to invert it here. I want you to feel stand like kind of over here so people can see. Alright, you're gonna invert, so hold it lower, so that when you invert it, the mouth of the can goes in the water. Go, 3, 2, 1, go. In the water, in the water. Oh! No, okay. So from the hot Okay. Good job, Andrew. Even if you didn't jump a little bit. Alright, so this is going to be our handy dandy assistant. Don't touch that right here. So, I know. Alright, watch closely. I have a magic trick for you. I can see convection, right? Okay, so Jess is going to hold the egg. Hold this egg. And we're going to basically full gravity. Ready? Alright, so you're going to spit it into the flask, but don't push into the flask. You gotta hold it like from the bottom, from the, right, don't let it fall. Wait for it. Wait for it. Like a, no. Why?
That is all because of the gas. Oh, that's true.
No, the fire stole the gas.
The fire was like, stick 'em up.
Carrie, can I get an educated explanation?
Oh no, I was just gonna ask how you were gonna get it out. No.
Just get that egg out and Oh.
Right here, your promises.
Oh, that's, I thought you were breaking it
I
down.
thought she was gonna throw it. Hit the top of the glass.
Nothing has happened.
Why don't you get a knife?
Why don't you do the fire thing
Use
again?
gravity.
She can use the fire thing again.
So usually I have to heat up the outside with a Bunsen burner
Yeah.
and let it like poop the egg out.
Let's do that.
At this point, it's staying in here first now. So can I get an educated explanation of why it's in there?
I'm gonna try that.
Okay. You gonna tell us a story about stealing things? Go ahead.
No. So the fire consuming the air that's in there, and so the pressure on the inside was lower, but the pressure on the outside was higher, so it like.
Okay, so the pressure on the inside, what?
It was
It was
lower.
lower than
what
Wait, can I-
the
can I-
outside.
The pressure on the inside. I'm listening to you and watching the show.
Oh,
I know. Be in there.
have your undivided attention.
Max.
That's all for, okay? You can pull it out now, okay?
It is intact.
Yeah, well,
Okay.
edible now.
It is yeah. Everything's edible. Okay. So let me draw it. Hey Chris, come back and join us. So here's the flask, and Max is going to try to explain to us in 30 seconds. Let's go.
Okay, but this gas really moves from areas of high pressure to low pressure,
Guys, be quiet.
and then infuses through the spaces, like inside, like the opening, and like as it does that, it propels like the egg with it.
Vacuum.
I'm gonna go with something that would be more related to what we've been talking about. Okay, so we have particles up here, right? Candle, egg, candles. Okay, so pressure of the atmosphere is out here. Pressure of the atmosphere is out here. What happened to the gas inside as the flames were burning? Okay, so we used up the oxygen. So what happened as we used up the oxygen?
The pressure is decreased.
Lesser pressure in here.
Then create a vacuum and suck the egg in.
So that's what Max said. So lesser pressure inside, and there was what was out here? Greater pressure outside. So it pushed the egg up. It didn't pull and suck the vacuum up. It was a push of greater pressure. Nothing sucks. Everything pushes. Okay. Cool. Moving on. Okay. Oh, I'm gonna hold off on that for a second. So.
Did you do the ideal gases particle?
So I kind of did on the last one, because we talked about IMF. So we talked about how ideal gases, we assume they don't attract, because if not, we get to account for pressure differences and volume differences because of these attractions. So we know that for real life, IMFs are at play, and so attractions can always occur, no matter polar or non-polar, they can occur. All right, so we use all this to set us up for success when we're doing the ideal gas law. The ideal gas law assumes all of these conditions are true about the kinetic molecular theory, and we get to use this equation. So I'm going to come back to this later. Right here. The ideal gas law doesn't have a whole scenario issue that the other gas laws have. So how many pressures do you see here? One. How many volumes? One. How many temperatures? One. So in all the other equations, we had 2. So it's a very obvious example when you're doing the ideal gas law because you won't see 2 of anything. And if you do see 2 of something, it's not the ideal gas law. So that's why this one's different than the ones we did yesterday. So because there's this R factor, R is a constant that helps relate all the variables together, and we call it the universal gas law constant. But look at all those units. What do you see? What's this? Atmospheres and liters and moles and Kelvin. So we see all those units. We actually have to mandate in the ideal gas law to use that unit of pressure, volume, and temperature, unlike in the other laws where you're like, hey, we can use millimeters of mercury, we can use kilopascals, we can use milliliters. So what do we have to use to match with the universal gas law constant? Pressure has to be in atmospheres, volume must be in liters, amount must be in, and if we don't have those, we can convert to them, right?
Yes.
Because if we don't have those and I plug it into this constant, or plug in that constant, what would happen?
Your ratios would be different.
Your ratios would be off, and you wouldn't be able to.
Cancel.
You wouldn't be able to cancel units, and that would be the end of the world, guys. You've got to cancel your units, okay? So, most important thing, cancel your units. All right, so we're going to do number 17. So that's after 16 that you just did the homework. We're doing 17 right now. So pull out your, who doesn't have this with them? Nick, do you have this? Elijah, pass this. Dust. Okay, so 17, here we go. Always in Kelvin. No question. Okay, so back with me. That's not a talk session. You with me? I'd like to be able to get through 17, 18, and 19. So let's do this. Okay, so 17. A student, this could be you, collects what?
25 milliliters of water.
Okay, so what is this? What variable? Volume, okay? At a temperature, I'm doing that in a second. I'm just going to write blatantly what I see here. At a temperature of
24 degrees Celsius.
okay, and then a pressure of 0.889 atmospheres. How many moles, so question moles, you should be writing down your givens with me, number 17. I'm not doing this for me, I'm just for you. Let's go. How many moles of oxygen did this student collect? And then secondary question, how many grams is this? And that's all. I throw the paper down, I don't need the paper anymore. So, I don't see 2 pressures, 2 temperatures, 2 volumes. This is not one of those normal gas laws. This is the ideal gas law. So then you look at that and you're like, okay, I know the ideal gas law. It's PV equals nRT. And you're like, what's that R value? Oh, I got it up here. What's the R value? 0.0821 atmosphere times liters per mole times Kelvin. Thank you, Rashida. You're my only one who cares. Okay, so the R constant is here. And I know I'm going to have to solve for moles, right? Well, I got pressure, I've got volume, I've got the R constant up in my head, I've got the temperature here. What am I solving for? N. And we know moles was in, right? So that's no question. How do I isolate N?
Divide by
Divide by what?
RT.
RT, because I need to get RT out of this N area. Correct? Correct. So R and T cancel. So what essentially does N equal?
PV over RT.
Tell me if you're with me here. Give me a thumbs up, give me a smile, give me something. Thank you. Okay, so this is our equation we're plugging into, right? Now, because my R is so specific, let's go back and double check our units. What should this be in? Liters, right? So this has to be what? 0.425 liters because you're backing decimal up 3 places. This has to be in,
Kelvin.
which is what?
297.
And is that fine? It's cool. Okay, what's our P?
0.8889 is here.
Oh, look at those units coming to life. What's my volume?
0.425 liters.
Oh crap, I think I forgot to video. Am I videoing?
You are.
No, I didn't mean that. Sorry. Sorry, interrupting the flow. Let's do this again. Keep going. R. R. Keep going. Noise and temperature.
297.
Woo! Okay, what cancels?
Liters.
Okay, I see liters top and bottom. Atmosphere, atmosphere. Kelvin and Kelvin. Leaving me with, and moles on the bottom of the denominator.
Wait, so even if we're on the same, like.
So it's because there's a fraction here.
Divide. You like do the copied out.
Oh, yes. So what we were asking here though is, this is a fraction in the denominator. This is the numerator of that. This is the denominator of that, so we can cancel the kelvins. And this is the numerator of the numerator. This is the numerator of the denominator, but still they can cancel. Same for liters. So the mole, which is in multiplying by the reciprocal, or copy dot flop, or whatever else you call it. We just like this thing comes back to the top. The denominator goes back to the top. So moles will be achieved as what? Calculate. Calculate. You have to put your numerator in parentheses and your denominator in parentheses if you're going to try to plug it in all at the same time. Your calculator cannot read your mind. Nope.
Just 2 years.
At this point, you're still going to get it wrong if you don't put parentheses. So tell me what's up when you get it.
Wait. Are these calculators?
Okay, I'm stopping there for a moment. Moles. Okay. Back with me. Squirrel. You guys with me? Okay, so this is your moles. That is the first answer, but this needs to be correct sig figs to what? 3 sig figs, round it.
0.0155.
Beautiful. And this is
Moles.
moles of what? It was oxygen gas if you read the problem. That is oxygen gas. Okay. Yes.
Does it matter if moles is on the bottom of the fraction?
So that's what happened. That's what you're talking about. When something's in the denominator of the denominator, and you do a copy dot, I'll put it to here, and you do a copy dotty floppy, it comes to the top. The one comes to the top. The mole comes to the top.
Okay.
That's a mole. That's a mole. It comes to the top. All right. Wait a second. I don't take any questions until I finish this question. Okay. So the last part, we got moles, right? This says go to grams. So what do we need to do? Convert to grams using what? Whoa, that's a big thing. Still really big. Periodic table. So we're specifically looking at molar mass of what? What kind of oxygen? Diatomic. Yes, it's a gas. It's a gas law. Good job. Oxygen gas, which is diatomic gas. And I'm going back to my original, so I don't have rounding error in between. I'm going just back to my calculator answer of moles of oxygen gas. And what is that molar mass? 32 grams of oxygen per 1 mole of oxygen. Answer 0.49 what? I'm gonna pick 6 grams, yeah. 3 sig figs. Woo, doggies. We're done. Okay.
Oh my gosh. I got a question. I thought we were doing this next Monday.
No, we're doing stoichiometry next Monday. We're doing gas laws today. Okay? Guys, stop whining. Stop. First of all, you're welcome for your education. You get a free education. No, you're good. Not everybody. I'm not talking to everybody. Stop whining. Put your big boy panties on. You got it. Okay? So go ahead. You have 5 minutes. Knock out number 18. And if I need to kick you out on spring break day, I will. Or I have a couple people that owe me detention, so they can have longer detentions. So go ahead and do number 18. I will tell you as soon as you get number 18 done. Please and thank you. I'll even write on the board.
Guys, focus.
Yeah, Austin